SwayamPrabha. Digital India. Educated India.
Hi, welcome back. So we were looking at possible problems or possible questionnaire that you can get. Of course, for a course like this, primarily it should be a a basic course to sort of get started on a future research area, right? So it's difficult to kind of just have a problem set, which is very typical, calculate numbers, etc. But yeah, well, we're just trying to see how best to look at this topic in terms of problem solving. So that's what we're doing right now. Okay, so we did a couple. So and let's look at another example, and this is something that we've studied in detail. All right, maybe it's almost like a relook at it, but let us do that. If I were to pose a question like that, how would you answer it? Okay, so let's look at that. So let's say now pressure gradient in the y direction of a turbulent jet is 0. Explain. Okay. So I think we've done this in detail earlier, but let's sort of take a relook at it. Okay. So pressure gradient in the y direction of a turbulent jet is 0. What do we mean by that? Okay. So the y momentum equation, let's write out the y momentum equation. Okay. Okay. There you go. So that's the y momentum equation, and as you can see that we are taking derivatives of the y component of velocity. So when I say y momentum equation, so I'm essentially looking at a Cartesian coordinate system, isn't it? And the flow is, so this is the velocity. Right, and since it's a turbulent flow, by definition, so then this is these are the mean quantities, and these are the turbulent quantities. These are velocity components that we are looking at here. Okay, and the pressure also, we take the derivative in the y direction of the mean pressure, right? So this is essentially the y momentum equation, right? Now let us see. So in that case, what if I take a look at this equation, what can we say here? Okay. Now, as we have said, as we have looked at it, and by this time we have established that the lateral velocities or velocities are very small in the y direction, right. This velocity, so v component of this component of velocity or y component of velocity is is very small compared to the u or the component of velocity in the x direction, right. So almost insignificant. So essentially what we are saying is that v component is really much small than this, right. So let us just say, since y component, or let us just say the velocity which is perpendicular to the direction of flow. So since y component of velocity direction perpendicular to direction of flow, right, is used in the x direction. Okay. Right. So because of that, what can we say? So then, so this means, right, this is 0. Okay. The derivatives in x and y directions, because the velocity component itself is very small, it's almost negligible. So we need, I am writing this why. Why am I writing this? I am writing this because these are terms in the y momentum equation, and so I am just using this by using this from the definition, right. Okay, then okay. Okay, so the primary component or dominant component of velocity, so this essentially means that the dominant component of velocity is this u mean, which is in the x direction, right, and v is the y component or the direction perpendicular to the direction of flow, right, and this v component is really very small compared to u, right. Okay, then again the gradients of quantities, right, in the x direction are minimal. Okay. So gradients of quantities in x direction okay. So these are minimal, which means, so this means gradients of quantities. So what we have here are these two terms. So you have this, right. So this is actually in the x direction, right. So gradients of quantities in the x direction is minimal. So we're basically saying okay, right. Therefore, what is left of the momentum equation? What is left of the equation? So then therefore y momentum equation is equal to Okay, so this becomes my y momentum equation. Right. So 1 by rho del p del y and del v square del y. Now, if you see here, so essentially all these terms just are removed from the equation, and only this and the last one, it remains, right. So now on what basis are we removing this? Well, these terms here, right. So these terms basically said the component of velocity which is most dominant is in the x direction, and the y component is therefore minimal compared to that. And using that, so we basically said these derivatives with these directions is 0, right. And also the second order derivative in the y direction, right. So because the value itself is very small, the value of v mean, right. Okay, and then we also have the second order derivative here, so which also we have written here. So a couple of first order derivatives, couple of second order derivatives, and what else? And that's it. Okay. Now the second thing is the gradients of quantities are the gradients of quantities are primarily again dominant only in the x direction, right. So x direction meaning the dominant in the y, the gradients of components are primarily in the y direction and not the x. So in that case, this term essentially is a gradient in the x direction, which is nearly 0, because essentially what we're saying is the sum total of the fluctuating components of velocity, right, is does not vary along the x-axis. It varies along the y, but not along the x-axis, and hence we take that out. So essentially what we're saying is these terms cancel. What is left out is essentially this one and the last term, and then we get this, right. This is the equation we get. Now what are we going to do about this? Well, we have a turbulent jet, right, turbulent jet. So we take two points. One is A, right, where the turbulence dominates, and one is far away, right, where so it's far away, which is B, right. This is here turbulence is minimum, right, such that turbulence is minimum such that, right. So here and it has free stream pressure. This is free stream pressure, okay, and this one is essentially far off, okay, turbulence domain. So basically we integrate between these 2 points A and B, okay. What did I write this for? Okay, so I'm saying I'm going to represent B by a circle, that's all, okay. So if I do that, so I'm going to integrate now, right, between the 2 points. Okay, so what we get here is integrate A to B okay, right. So if I do this, or integral okay. Okay, right. Now the point, what did we say? So A is the point which is, right. So B is the point which is at infinity. So this is where it has free stream pressure, right. So PB we can write as this, okay. Now this point B is far away, is from the jet, right. So here the turbulence is negligible or almost zero. So therefore V dash, which is the fluctuating part of the component of velocity, is going to be zero, right. So we can write that. So then this becomes okay. So or okay, and or is this, right. So correct. Okay. So now basically A is a any point, and it's an arbitrary point. So I can remove the A and just write this as the velocity at any location, right. So I'm going to write this, or so essentially this by rho is 1 by rho okay. Now this is my then the equation, or this is the relation which the mean pressure will hold. And what I can see here, that there is actually no dependence in the y direction, but there is direction, there is no dependence of this pressure of anything in the y direction from what I see from here. Okay. However, the question was pressure gradient in the y direction. So let us see what it is going to tell us. The pressure gradient is going to be 0. So there is nothing. So here what we can see is that the pressure in the y direction at a particular location is actually, if you see, is not changing. Right. So then let us let's take a derivative. There you go, right. So, this is equation 1, and we are going to take a derivative of this. So, if I do that, okay, this, right. So, definitely the free stream pressure, right, is not a function of y, right, and only x. So, P infinity does not depend on y, it depends only on x. In that case, what do you think of this term, right? So, this term is going to go to 0 because del del y of P infinity x is going to be 0, right. So, that term goes to 0. So, we are left out with this, right. Now, when we are slightly far away, when we are slightly far away from the jet, so anywhere turbulence is negligible, and then V dash square bar is going to be 0, right. So, second term is also 0. Now, at the second term, which is okay, right. So, in that case, so essentially, so which means that del, so the gradient of pressure in the y direction, right, is 0, right. Now, so del P del y, right, this is 0, this is 0, or we haven't yet established, yes, so we said that, right. So, both the terms on the right hand side will kind of go to 0, and so gradient of pressure in the y direction is 0, right. Yeah. So, now this is the derivative of the pressure, of the mean pressure. Now, what if right, we were not like, well, no, not really, I think this is okay, all right. Okay. So, that is something we had to sort of work out and see for ourselves. So, pressure gradient in the y direction of a turbulent jet is 0, explain. So, I basically said that this is your y momentum equation, and that is that, right. And from there, we are able to see that the pressure, the mean pressure is given by this, okay. And then finally, we see that del P del y is 0. All right. Okay. So, this is now, do you see what kind of inference do we draw from this when we do something like this? We've been talking about this for some time now, right. When we make these assumptions, or when we consider this, and so we are looking at 2 points, which are, one is where turbulence is dominant, other places where turbulence is not dominant, and we integrate between the two and the equation, right. And so then, okay, now this behavior that you just saw here is similar to a boundary layer also, right. Now, I think we'll sort of talk in detail about that when we get there. Okay. Now, this is true, right, and this is similar to a boundary layer. Okay. So, I think we'll stop there, and we'll take up something interesting. We'll take up another, another little piece of problem, and we will look at that. Okay. So, let me sort of show you a plot first, and then we'll go back. So now if you see here, right, in this plot, okay, so you have the U jet, okay, so you have U jet which is coming out, and this one is H, or you can call that as D, right, this is a potential core, right, and then when the fluid is moving, right, and then this is a fully turbulent jet flow. Now this is a location delta where you have the U naught is the central line velocity, and this velocity is half of central line velocity. So this delta is essentially representing the jet half width, right. So that's by definition. So at the half the width of the jet, basically the velocity is equal to U half of the central line velocity. Right. So I'm going to use slightly different kind of notations from what's being used here. For example, free stream, it's going to be U infinity, okay, instead of just 1. Okay. So let us look at this. Okay. So what is the question here? So the question here is, now for the plane jet shown, so for the plane jet shown, okay, draw a mean velocity profile. So draw a mean velocity profile before and after the locations of the velocity profile shown. The locations of the velocity profile, yeah, shown. Okay. All right. Okay. So let's see, what are we talking about here? Okay. And you're almost wondering what sort of a question is that? Okay. So I have this, so this is a jet which is coming in, right? And there's a velocity profile which is shown here somewhere, you know, the kind of developmental length is all done and everything. So we have a fully turbulent jet flow in this region, and the velocity profile is shown, right? Now if I had to draw a velocity profile just before and after this location, how would I draw it? And what should I consider when I say that? What do I mean? What should I consider? Now two things here. One, the first thing that I would want to know is that what will happen to U naught? Will U naught decrease or increase as I move, you know, as I when I'm before this location and when I'm after this location, right? So what will be the value of U naught rather, right? The central line velocity. And the next question is this location delta where the velocity is half the mean central line velocity. Will this length or height remain same? So if I go to a location just before this location which is shown, so will the delta be more or less, right? So these are some of the questions we need to answer first before we can go ahead and draw, before we can actually go ahead and start drawing the velocity profiles, right? Okay, so well, now this is something again, something that we have done earlier. So I'm going to just sort of do a reminder of that. Okay, this is something we've done in detail before this. Okay, so this is right, mean velocity by the jet velocity and x by d. Okay. So, we had, I do not know if you remember, so we had this. Okay. I had that, right. So, these are essentially mean velocity profiles or mean velocity profiles against x by d, and this one was for x by d equal to 30, this is x by d equal to 60 and x by d equal to 100, right. And okay, now if I had to draw this, so say for the red plot here, this is the total spread. So then if I go from half right, so this is going to be r half basically, right. So this distance is going to be right, r half. So similarly, when I go to the for x by d is equal to 60. So when I am x by d is equal to 30, meaning that is at certain x location after the jet has come out. So and then x by d 60 means I am going further down. Right. So r by x is going to be this. So as you can clearly see now, as I can clearly, you can clearly see that r half will in this case if you see r half is increasing with as we move along the axis, right, axis of the jet, right. So or sort of increase in x. Now u naught, right, u naught, which is the center line velocity. Now these are the inferences we get, right. Inferences. Okay. So number one inference is that u naught, right, decreases with increase in x, right, and r half of x actually increases with increase in x. Okay. So this means, so here what you see here is that these three profiles that I've drawn here, right, now they're changing in x, right, but they don't change their shape, right. Now these are the profiles, right, with change in x, but the right. So, but the shape remains unchanged, right? The shape does not change, right? So, then how should I draw this? So, let's go to, okay, we can do it here also. Okay. So, then let me draw this figure here. Okay. So, let us just say the first this is what is given, let us just say that. Okay. So, if that is that, then this is delta, okay, and is the centerline velocity. This is the centerline velocity, right. Now, so let us choose a location which is, say, here. And this is a location which is here. How shall I draw this? How shall I even draw this plot? Well, the first things first, we said that u naught decreases, which means, look, let us name these locations. So let's say this is O, right, and let this be P, let this be Q. These are just the locations, right. Now, we said that with increase in x, right, so this is my x actually. Okay, with increase in x, u naught decreases, which means that at location P, u naught is going to be higher than what is shown here. So let's just draw a plot like that. Okay, that, and then if I'm going to draw the line, okay, so this is the profile at P. Okay, and okay, I think I did not write this here. So this is the location delta where you essentially have half the velocity, and we also found that r half actually increases with increase in x, which means that here at P, r half is going to be less than what it is at O, right, at the given location basically. So which means that right. So this is my r half delta, right, and here we have centerline velocity, which is 1/2, so 1/2 of the centerline velocity, right. So I think you can do that, draw it for the second location also, but I'll go ahead and just do it. So then here, so we know that u naught is going to decrease. So now what the u naught should be less than what it is in the black one, so it's going to be like that. Right, so that's the velocity profile, okay, and r half increases, right, r half increases. So then we will have an r half which is something like this. So r half, we will keep it like this, right, and this is the delta, right, and it's here that you have the centerline velocity, right. So let's just say that here, so I'm going to sort of write it out properly. Okay, let's just say here, so u naught, say x1 by 2. Okay, and this one is going to be, say this is x1. X naught, and this is x2. Okay, so this is fine, and then this is x2, so therefore this, so we can actually write this also. Okay, so let's just say, okay, okay. Right, this is u naught at x naught. Okay, so similarly, so u naught x1. Okay, is equal to u naught is x2, right? And so this, what we're saying here is this is u naught x2 by 2, right? So I think that's all really the way I can draw this, right? So it was very simple, right? So usually when you see if you see something like this, right? So you see this velocity profile. Now the thing is, if you see just this velocity profile, can you plot it, plot a couple more lines like this, and whether you're going down or going slightly back? I think that was the that was the question, and that was the attempt to see how, if we had to do this, how will we sort of go about it. So I think that's that really. So here there is math, but first we understand the problem, the physics of it, and only then the math can be done. So this is a classic example of that, that if you just put numbers in there, it's not going to help. You should actually know what is, how things are evolving really. Okay, so all right, so essentially, so that, okay. Now we could have like a couple more questions to ask here. I think we're going to run out of time here, but I'm going to just touch upon it, and then we'll take it up in the next class. Okay, so let's go here. So we could just say, okay, let's just see what they do. Okay. What is delta? Okay, so mark such deltas on the velocity profiles plotted, right? We've actually done that. What is its significance? Okay, so if I go back here, so draw the delta. So we've drawn the deltas here, right? So we basically said this height is essentially increasing. So if you see, it is increasing, and I'm going to do okay, say a green line. So let's just say I'm connecting this, right? So this is the height, something like that, right? So this is the delta that I'm talking about. Okay, so delta is increasing as we move along x, right? That's what we see. What does this signify? What does this signify? R is increasing as we go along x, which means that the jet is spreading. This is a jet half width, right? Is the half width. So this is basically telling us as to where exactly is it located, right? Or till where exactly is my turbulence flow dominant. So therefore, that exactly is its significance. So this is an important parameter basically to calculate, and we do that here, right? And this is how delta looks, right? And this is basically delta. Now this is again something. The next question. This is something that you have done. Okay. So if you see this, what I just did, I purposely drew this. If you see this, right, if you see the turbulent flow and then the properties which matter. So for example, the center line velocity, right, now that varies along x, right, but there's no variation in the y direction. Now what about, and then, so if we draw the plots like that, and then we see that the thickness, right, at the thickness or the location at which the velocity is 1/2 of the center line velocity. So that is by definition the jet half width, right? And it essentially is defining me as to the spread of the jet, and it's seen that increases. Now does this picture remind you of anything? Okay. Now, that will be the question if I look at this picture here. This is a case for turbulent flows, but does this ring a bell, or is it something that you've seen, or do you find anything that from this plot? Okay. So, I am going to write this down and leave you to sort of ponder over it. So, what are the similarities right? What are the similarities of the fully turbulent jet shown? Well, it is shown, so I am going to write that. Okay. So, what are the similarities of the fully turbulent jet shown okay, with a boundary layer, right? Draw such a boundary layer for the same jet. Okay, so draw such a boundary layer for the same. So, this is something I am going to leave you to it and see if you can do that. So, this is a turbulent flow, right, what we are looking at, but it seems to have similarities with the boundary layer. Boundary layer also you have a velocity which is dominant in the x direction, and all the differences are primarily concentrating on the in the y direction, right, and the thickness of the boundary layer. So, thickness is the layer till which the viscosity is confined, and beyond that there is no boundary layer, right. So, the viscosity effects are it's sort of very, very small or almost not there as we go away from the surface on which the boundary layer is developing, and the delta is basically the thickness of the boundary layer. So, within that delta the viscosity coefficients are not negligible, but beyond that they are, right. So, this is something we can discuss a little bit next time, but we should be able to answer this one though, right. What are the similarities of the turbulent jet with a boundary layer, and draw such a boundary layer for the same. Okay. So, I think we will take this up in the next class. For now, I will stop here. Okay. Thank you.